So let's kick off this explainer with a question that honestly drives a lot of chemists crazy when they first start looking at standard NMR. How do we actually, see a molecule's true three-dimensional structure? Because standard NMR is fantastic, right? It tells us exactly how atoms are connected to each other through their bonds. But molecules aren't just these flat 2D drawings on a whiteboard. They twist, they fold, they take up actual physical space. So how on earth do we measure the actual distances between atoms across that empty space?
Well, welcome to our exploration of NOE different spectra. Today we're going to see how advanced spectroscopy basically acts like a molecular detective to unlock those hidden 3D shapes. We'll be using advanced enhancements, specifically the nuclear Overhauser effect different spectra to determine the exact 3D spatial location of protons. It is super cool. Here's our quick roadmap for today's explainer. We'll start with the missing dimension in standard NMR, meet the dipolar phenomenon, learn the brilliant subtraction trick that makes it all work, solve a molecular puzzle, and then zoom way out to see how this applies beyond just simple molecules. Okay, Section 1, the missing dimension and the limits of standard NMR.
This really gets to the heart of the matter. Standard through-bond coupling relies on the electrons inside the chemical bonds to pass spin information along. It maps out a 2D network of connections. It tells you who is holding hands with whom. But through-space dipolar interaction, which is the engine behind NOE, maps 3D proximity. It shows us which protons are literally just sitting next to each other in space, totally ignoring the chemical bonds between them. They might be 10 bonds apart, but if they're folded up next to each other, this effect sees it. We absolutely need this different phenomenon to get that through-space measurement.
Moving to Section 2, the dipolar phenomenon. Let's officially meet the nuclear Overhauser effect.
Let's break this definition down, because it sounds like a lot of jargon, but the concept is actually beautiful. The nuclear Overhauser effect happens when we blast or irradiate one specific group of nuclei with a radio frequency. Doing that actually alters the spin state population of the nuclei hanging out nearby. The key here is that the magnetic moment of that nucleus we zapped exchanges energy with its neighbor through space. It literally forces its neighbor's spin state to shift into a lower, more favored energy level. And just to be clear, we aren't talking about electronic dipoles here. These are magnetic dipoles processing in a magnetic field, trading energy directly through space.
Now, I want you to burn this number into your brain, 4, because this dipolar effect is incredibly strict. It limits our through-space interactions to protons within about 4 angstroms of each other. The physics is just completely unforgiving here. The strength of this dipolar effect drops off exponentially, specifically as the inverse of the distance to the 6th power. Think about that. If a proton is even a tiny bit further away than 4 angstroms, the enhancement essentially vanishes into nothing. It's what makes this technique such an unimaginably precise molecular ruler.
Section 3, the subtraction trick. Let's look at the math behind the magic.
So to actually use this super precise 4 angstrom limit in a real lab, we use a ridiculously elegant mathematical trick inside the spectrometer. Step 1, we tune the decoupler frequency to exactly match our target group of protons, and we irradiate them. Step 2, we run a control spectrum under the exact same conditions, but we set the decoupler frequency way off in the middle of nowhere, what we call off resonance. Then step 3, we literally just have the computer subtract the 2 digitized spectra from each other. By taking the saturated spectrum and subtracting the perfect control, all the normal, messy background signals completely vanish.
What you're left with after that subtraction is just a totally clean slate. The proton we purposely irradiated shows up as a massive negative signal, pointing straight down. And any positive peaks, the ones pointing up, represent exclusively the direct 3D spatial neighbors of our target, the ones that caught that energy boost. If a proton wasn't inside that magic 4 angstrom bubble, it simply subtracts out to a flat 0. It's so clean!
All right, Section 4, solving the puzzle. Let's apply this detective work to the ethyl methyl methylate mystery.
Take a look at this baseline. This is the standard proton NMR spectrum of ethyl methyl methacrylate. It's crowded, right? We've got distinct peaks. But just looking at this 1D trace, the actual 3D geometry of those alkene protons is completely ambiguous. We know the atoms are there, sure, but are they pointing toward the methyl group or away from it? Standard through-bond coupling leaves us guessing.
But then we apply our subtraction trick. We zap the methyl group right at 1.9 ppm. See that huge negative peak diving downward? Now look at what's left. Only its absolute nearest 3D neighbors light up as positive peaks, perfectly isolated from the noise. Everything else is a flat line. This is definitive proof of exactly which protons are physically sitting next to that methyl group in 3-dimensional space.
And we can play this game all day. Let's run it again, but this time we irradiate the proton down at 6.1 ppm. Boom! A new negative peak, and an entirely different set of positive peaks instantly pop up. We've just identified a completely different 3D spatial neighborhood within the exact same molecule.
So, let's round up the key takeaways from this detective work. A negative peak is your target, the one you zapped. Positive peaks are the physical neighbors within that 4 angstrom radius. A flat baseline means absolutely no spatial interaction happened. Following these rules gives us a foolproof way to map a molecule's stereochemistry. No more guessing based on overlapping standard signals. If you're wrestling with tricky E and Z alkene isomers, NOE difference spectra give you the absolute, undeniable spatial evidence you need to solve the structure.
Finally, Section 5, Beyond Simple Molecules. From molecules to the human body, because this goes way beyond the chemistry lab.
When you zoom out, the real-world impact of this is just staggering. What we're talking about is the exact same fundamental physics used in an MRI scan. The principles of proton spin, magnetic fields, and relaxation times that let us perfectly map ethylmethylmethylate, those are the exact same principles that allow doctors to non-invasively map the soft tissues inside a human skull. We're essentially just looking at water and fat protons inside a much larger, way more complicated biological flask.
Which leaves us with this pretty wild thought. If these advanced NOE enhancements can act as a molecular detective to perfectly map a single microscopic molecule in 3D, what else are we going to discover as we push these exact same quantum principles deeper into complex biological systems? It's literally mind-blowing that understanding the quantum spin of one tiny proton opens the door to everything from drawing chemical structures to saving lives in a hospital. The universe plays by these fundamental laws, and learning how to read them through advanced enhancements lets us literally see the invisible. Thanks so much for joining me for this explainer, and keep questioning what you see.